Hello guys, welcome back to my channel, Math and Universe. Today I will discuss about very famous result in mathematics, that is the solution of the Basel problem. So first, this solution was given by mathematician Leonard Euler, and the result was very beautiful. Indeed, it is very beautiful because the result is this: the sum of the reciprocals of the squares of natural numbers is equal to pi square by 6, right? So it is indeed a very beautiful result. So how did Euler prove it? And today I will not show you the proof that is done by using Fourier series. Rather than I will focus on how Euler did it. And I was very excited about this video also because the technique of Euler to approach this proof was very interesting. So get into it. So first, Euler observed the graph of sine. So this is the graph of a sine function. Am I right? So in this graph, Euler then searched that which points are the zeros of sine function. So what I mean by zeros? So if we mathematically write this graph's representation, so we will write y equals to sine x, right? But we have to find zeros of our equation. So what was the equation? We have to find out. So sine x equal to x. This equation is only true when x is equal to 0. So we found a 0 or a point where this equation is satisfied, right? So x equal to 0 and this equation will be satisfied, right? Then Euler find another point where we can make this equation 0, but we have to multiply a thing to make this equation 0. So what it is? We have to multiply it by 1 minus x by pi. If we put pi in it, this portion is 0. And when we put pi in here, this portion is also 0. So we are good to go. Then we can put from this portion, we know that here is 0, here is pi, here is 2 pi, here is 3 pi, and so on. So on the zeros till positive infinity, right? And here we know that this is negative pi, this is negative 2 pi, and so on till negative infinity along the negative x-axis. So when we find a zero at this point, right? So we have to we can find a zero from the negative pi. Am I right? We could multiply a product like this by pi. Right? If we put negative pi in here, this will be 0. We know from the behavior of the sine function, and when we put a negative pi, this portion will be 0 and the right hand side will be also 0. So we are good to go here. And then like this, we could put 1 minus x by 2 pi, 1 plus x by 2 pi, and 1 minus x by 3 pi, 1 minus x by 1 plus x by 3 pi, and so on. So Euler made this beautiful product that will come a very handy later on to solving this problem. So if we multiply those, we write x into 1 minus x squared pi squared. We could formulate this using a minus b into a plus b formula, that is a square minus b square, right? Then this thing will be x squared 2 pi whole squared. Then when we multiply these two, we can get minus x squared 3 pi whole squared, and so on. Right? So we can multiply those, and I will skip a little because the multiplication will cost some time. So in order to shorten this video, I will write the important parts of this product, and other else I will denote by a single symbol. So let's get it. X. If we multiply these two and these two, these three, if we multiply, we can get 1. If we multiply all these, we can get 1, because we have 1, or we have 1 in each factors, right? So if we multiply 1, we can get 1. Then if we multiply x squared by pi squared to this and this, because if we multiply x squared by pi squared to this, then after multiplying this, we can get we are getting a we are getting a result. Then we are multiplying these two products result with this. Then also we can get x squared by pi squared, right? So we can write it like that, x squared by pi squared. Like this, we can do this. We can do this likewise, minus x squared by 2 pi whole squared minus x squared 3 pi whole squared. Likewise 4 pi whole squared. And all these till infinity, and we have some extra terms. We have some extra terms that are powers of x to the power 3 or bigger. Okay, so we will denote it by big O of x cube. Okay, the remaining terms that are whose exponents are bigger than 3. Okay, these are denoted by the big O of x cube. Okay, so if we multiply x in those terms, we can get x, and we multiply them, x cube, into, we can common out 1 by pi squared. We can common out a pi squared, 1 by pi squared. Then we can get 1 by squared, 1 by 2 squared, plus 1 by 3 squared, plus 1 by 4 squared, plus till infinity. Plus big O of. So, if you recall the Basel problem, we know that we have to find out the sum of n goes to 1 to infinity, 1 by n squared, or we could say the reciprocals of the squares of the natural numbers, that is them. Am I right? We found this. So we could write like x minus, x cubed into 1 by pi squared into the sum where n equals to 1 to infinity, 1 by n squared, plus O x to the power 4. So we got this expression. So I have to erase these things for spacing of my board. So we know from the Maclaurin series expansion of the sign that sin x equals to x minus x cubed by 3 factorial plus x to the power 5th by 5 factorial minus till infinity. Right? So if we equate coefficients, because it is sine and it is also sine. So we can absolutely equate coefficients. So this coefficients is equal. So we have to equate coefficients only find out the value of this. So we have to equate coefficients of x cube, right? So if we equate coefficients of x cube, we can set equal to this thing with this thing, right? This thing with this thing. So as this 1 by pi squared into the sum of, this is a very disastrous sign of the summation. So the sum, oh shit, I'm very excited. So I'm writing n equals to 1 to infinity 1 by n squared equals to. So the coefficient of this is 1 by 3 factorial, right? So if we multiply both sides by pi square, we can get n equals to 1 to infinity 1 by n squared pi squared by 3 factorial. But what is 3 factorial? We know that 3 factorial is equal to 6. So we have proved the famous Basel problem using Euler's method. We proved it like Euler did in his first attempt, right? So that was a very interesting journey to this proof. So I hope you like this approach of Euler, and personally this was a very interesting journey with this proof, and I love this proof very much. This Basel problem is another proof that is using Fourier transform, so which is a very much difficult than this proof of Euler. It was a very straightforward proof of this beautiful result. So that's for today, and thank you for staying here with me. And if you enjoyed this video, please like and subscribe. Recommend me like if you like, and please encourage me that I can make videos of very interesting math problems and show them to you in the near future. So thank you very much for viewing this very interesting and beautiful result. So that's for today. Goodbye.